We're going to look at area under curves. Now, previously what we did is we found the area under a velocity curve, and we related that to displacement. Here we're going to look at specifically a derivative function, and we're going to find out what that area is, and we're also going to try to figure out what that represents. So this function that I've drawn here, this is this cubic function, and that's that black curve there. And we're going to use rectangles to approximate that area under the curve. So we're going to do that. We're also going to try to figure out how are we going to get an exact area? Because you can see that with these rectangles that we're using, it's not really quite exact because it's really hard to fit rectangles in curved spaces. So this is what we're going to attempt to do today. So the area is going to be approximated at first with these rectangles. So each one of these rectangles is going to be the height, which is the height of the curve, or the y coordinate of the curve, times the width of those rectangles, which we can arbitrarily choose, and those areas we're going to add up. So here I've given you the y coordinates of that f prime graph, so that cubic function, x cubed minus 4x squared plus 3x plus 5. We've been given x coordinates and also the y coordinate, or how high that graph is. And we're going to calculate the area of each one of those rectangles. So for the first rectangle, we have the height of 5, and since the area width we've chosen to be 0.5, we're using 0.5 as our area as the width of the rectangle. The area that we're going to calculate here is 2.5 square units. For the second rectangle, we have a height of 5.625 when we plug in 0.5 into that. And here we're using the left edge height. The area that we're going to calculate is going to be 2.8125. Here we get 2.5. When we multiply this height by 0.5, we're going to get 1.9375. And here we get 1.5. And here we're going to get 1.5625. Okay, and then using our calculator, we can add this all together, and we should get 12.8125. That's going to be square units. Okay, so that area under that curve, we're going to say is approximately 12.8125. So how can we make these approximations better? So how can we make this area, these rectangles, fit better and better under that curve? Well, we can do that by we're going to let our delta x approach 0. Okay, the thinner those rectangles are, the better it's going to fit that curve. And if we let those rectangles essentially go to 0, we can pretty much fit the curve perfectly. And so the value of delta x that would give the best approximation of the area using this method would be delta x equals 0. Well, we know we can't let that happen because if the width is 0, we'd have no area. So we're going to do this. We're going to use a limit and let our delta x go to 0. So with a limit, we're going to be able to figure out exact area. So we're going to let for our f of x times delta x, okay, and that's going to give us exact area.